Imagine a vehicle that does not fear the desert. A machine built to glide over mud, climb jagged volcanic rock, and slice through forests where roads don't exist. Now imagine Maxwell, a man obsessed with innovation, walking into a private testing facility where these machines aren't just concepts, they're real. Welcome to the future of off-road tech. Maxwell investigates next-level machines. And trust me, what he's about to uncover is years ahead of anything the public has seen. But before we follow him inside, here's the first twist. These vehicles were not designed for consumer adventure. They were engineered for autonomous exploration, missions where humans can't go, or shouldn't. As Maxwell steps through the reinforced gates, he enters what looks like a hybrid between a laboratory, a hangar, and an alien autopsy room. Technicians are quietly monitoring screens showing terrain models, collapsed cave systems, Arctic frost plains, and deep uncharted rainforest pockets. Parked in the center is the first prototype, a six-wheel, torque-vectoring crawler with articulated suspension that bends like the spine of a reptile. No steering wheel, no pedals, just sensors, LiDAR clusters, and a neural drive system that maps terrain in real time. Maxwell circles it, studying every joint in the chassis. The engineers explain that each wheel isn't just powered, it has independent compression logic. Meaning when one wheel sinks into mud, the system calculates pressure loss and redistributes torque instantly, faster than any human driver could react. Then comes the part that leaves Maxwell speechless. They hit a command on a tablet, and the crawler shapeshifts its suspension, lowering the center of gravity until the frame practically kisses the ground. It's preparing for stealth mode, designed for reducing thermal signature during defense operations and wildlife research. Maxwell raises an eyebrow. If this is the entry-level model, he says, what does level 2 look like? The engineer smirks, motions him forward, and they take him deeper into the facility. Here sits a machine that looks nothing like a vehicle, more like an insect. A multi-legged rover, with titanium limbs and gyroscopic balancing cores. Its purpose? Navigating landscapes so unstable that wheels would sink on contact. Maxwell watches as it steps onto a platform covered in loose gravel. Instead of sliding, it analyzes grain density and adjusts its footing, almost like a mountain goat on ice. But the real breakthrough isn't how it moves, it's how it thinks. The rover uses predictive topography mapping powered by terrain AI datasets gathered from volcanic zones, collapse mines, and Martian simulations. As Maxwell listens, something clicks for him. These aren't vehicles built for thrill seekers. These are machines preparing for a future where off-road doesn't mean adventure, it means survival. Just when he's about to ask about power consumption, the lead engineer interrupts with a quiet warning. This next prototype, we don't test it indoors. He gestures toward a massive cargo door that opens into a private outdoor track surrounded by cliffs. Dust swirls in the distance as something heavy moves behind the ridgeline. Maxwell steps toward the edge, shielding his eyes from the sun. What emerges next looks like a fusion of military engineering and sci-fi imagination, a towering hybrid electric exotruck with retractable claws for anchoring on rock faces. It moves with a mix of brute force and robotic precision, leaving Maxwell stunned. And then, without warning, the machine accelerates. Not on wheels, but on adaptive traction plates that dig into the earth, giving it the climbing ability of a tracked tank and the speed of an ATV. Maxwell watches in disbelief as it scales a near-vertical slope, showering the valley in rocks. He finally manages to shout over the noise. Who built this? The engineer answers without taking his eyes off the machine. A joint project, Defense Research, Industrial Robotics, and an African inventor whose name you probably know. Maxwell's expression freezes. There's only one name that fits. But before he can confirm it, a siren sounds through the facility, and the machine suddenly powers down mid-climb, clinging to the cliff like a metallic predator lying in wait. The engineers exchange worried looks. Maxwell turns to the lead technician. Is that supposed to happen? The technician hesitates, and then says quietly,
No.
And that's exactly why we brought you here. As the dust settles, Maxwell meets the engineering leads behind this machine. One explains that their core philosophy isn't just strength, its survivability. The vehicle is designed around a reinforced exoskeleton rather than a traditional ladder frame, allowing it to maintain structural integrity even during rollovers or direct impacts. It's a blend of aerospace and automotive design that leaves Maxwell clearly impressed. But what comes next is something he never expected. The team takes him into a testing bay where a massive platform simulates uneven pressure points beneath the tires. Maxwell watches as the vehicle adapts in real time, its suspension extending and retracting like a living organism. Every wheel moves independently, allowing the frame to remain level even as the ground shifts violently beneath it. One of the engineers laughs and says, "Flat ground doesn't exist in the real world, so we stopped building for it." Maxwell then asks the question many viewers are already thinking. If this tech is so advanced, why isn't it commercial yet? The answer is both surprising and sobering. High-end off-road innovation isn't held back by technology, it's held back by economics. These machines are incredibly expensive to build, test, and certify. They're capable of replacing entire fleets of specialized vehicles, but only governments and industries with extreme operational demands have the budgets for them. Still, Maxwell sees potential beyond price tags. He points out that many major breakthroughs in history began as military or industrial tools before filtering down to civilian markets. Computers, GPS drones, night vision, and now adaptive terrain vehicles. The only question is when, not if, it happens. The tour continues into another chamber where prototypes await final evaluation. One stands out, a compact off-road exploration unit barely larger than a side-by-side, but engineered like a tank. According to its designers, it's meant for scientific expeditions in places where rescue is impossible and communication is unreliable. It carries weeks of supplies, autonomous navigation capabilities, and a thermal power system that keeps it operational even in frozen conditions where batteries would normally fail. Maxwell climbs into the cockpit and immediately notices the difference. No flashy UI, no consumer-friendly styling. Just rugged, essential controls made for experts, not influencers. This isn't a recreational toy. It's a survival tool. The engineers show him historical footage of these machines crossing deserts where no roads exist, scaling slopes that defeat even modified 4x4s, and navigating flood zones filled with debris. Maxwell quietly reflects on a point few people consider. While most of the world builds cities, industries like mining, construction, emergency response, and science operate in the blank spaces on the map, the places technology isn't built for. These off-road machines are filling that gap. Before wrapping up the field segment, the team brings out their final demonstration, a remote-controlled heavy transport carrier designed to haul materials across landscapes too dangerous for human drivers. Maxwell watches as it pulls a payload through mud, over jagged rocks, and across a riverbank, without a person inside. It's slow, deliberate, and astonishingly reliable. Maxwell comments that this could change everything for disaster recovery and conflict zones. No drivers, no casualties, no delays, just automated logistics where humans can't go. And just when the audience thinks the tour is over, Maxwell reveals there's one more facility to explore, one that may hold the key to the next generation of off-road power systems. Because while suspension, armor, and autonomy are evolving fast, the biggest bottleneck remains energy. Where do machines like these get the power to operate for days, weeks, or months in environments with no infrastructure? The answer could redefine not only off-road tech, but the future of remote exploration entirely. Maxwell takes a deep breath, turns to the camera, and says, "We're heading to the Power Lab. And what they're working on might change everything you think you know about energy in extreme environments." Maxwell steps through a set of reinforced doors and enters a quieter building where the sound of engines and hydraulics fades into the background. This is the Power Lab, a place that looks less like an off-road facility and more like a fusion between a physics research center and an aerospace prototype shop. Rows of test benches line the space, each holding strange devices wrapped in insulation, cooling tubes, and monitoring cables. Unlike traditional automotive labs, there are no fuel canisters stacked in the corner and no EV charging stations buzzing under load. Instead, The team is experimenting with hybridized energy solutions built for isolation, endurance, and autonomy. One of the researchers rolls out what looks like a small, sealed reactor core, no bigger than a suitcase. It's not nuclear, not chemical, and not a conventional generator. It's a thermal conversion unit that uses temperature differentials to produce electrical power with minimal moving parts. In extreme cold, where batteries can drop to 20% capacity, this system thrives. It feeds off the environment instead of fighting it. Maxwell leans in, fascinated. Most viewers have heard about solar, diesel, fuel cells, and batteries. But thermal gradients? That's a new battlefield. The researcher explains that on Earth and on other planets, temperature imbalance is everywhere. From deserts to tundra, the difference between day and night or surface and subsurface can be harnessed as an energy source. It's not designed for cars zipping down highways. It's designed for machines that crawl across unknown territory for weeks without human support. Next, they unveil another technology, modular power capsules. These are ruggedized battery cores that can be swapped in the field like ammo magazines. Instead of waiting hours to recharge, an expedition team can carry multiple capsules, each armored, weatherproof, and compatible with both ground vehicles and aerial drones. The idea isn't just endurance, it's synergy. The same energy system supports multiple platforms, reducing supply chains in dangerous environments. Maxwell asks how all these innovations compare to hydrogen, a favorite buzzword in clean energy circles. The team doesn't dodge the question. They explain that hydrogen is promising for civilization, but terrible for isolation. It requires production, storage, compression, and stable infrastructure. Out in the wilderness, those things don't exist. So instead of chasing what works in cities, they're building what works where humans have no business being. One engineer points to a rugged demonstration unit, a tracked exploration rover powered by a compact hybrid system using thermal, kinetic, and battery reserves. As it moves, the suspension and track mechanisms harvest micro amounts of energy from vibration and motion, feeding it back into onboard storage. It's the same principle behind regenerative braking, but applied to crawling, climbing, and rattling across brutal terrain. Every bump is fuel. Maxwell notes that nature never wastes motion, but machines usually do. This rover flips that idea. Nothing is wasted. Nothing is ignored. Then there's the most secretive corner of the lab, shielded by privacy panels and guarded by technicians. A senior researcher explains only on the condition that nothing beyond general concepts will be shown. The team is experimenting with compact radioisotope-based heat systems, not weapons, not reactors, just miniature heaters that produce stable warmth for decades. They're already used in space probes like Voyager and Mars rovers. Now the question is whether Earth-based exploration machines can leverage similar concepts safely and economically. Maxwell looks stunned. Most people think of off-road tech as big tires and loud engines. But here, the future looks quiet, slow, methodical, and almost biological. Machines that don't roar, they endure. Machines that don't demand fuel stations, they create their own stability from the environment. Before leaving the lab, Maxwell asks the final question viewers are screaming at their screens. How soon until this reaches the real world? The lead scientist smiles and answers carefully. Industry demand is rising. Mining companies, scientific institutes, emergency agencies, and even space organizations are watching closely. When machines move into places where humans can't, something remarkable happens. Data increases, risk decreases, and progress accelerates. Maxwell walks back outside, processing the bigger picture. This isn't just the future of off-road machines. It's the future of remote work, autonomous exploration, and planetary deployment. Earth is the testing ground, but the technology points upward. He climbs into a transport vehicle as the camera follows, dust swirling around the wheels. He notes that there's still one more part of the story to uncover. The pilots and operators who push these machines to their limits, shaping the designs with real-world experience instead of theory. Because no matter how advanced a machine becomes, the frontier is still controlled by people who know how to survive it. Maxwell arrives at a rugged training ground located several kilometers from the main complex. Here, Technology meets the unforgiving elements. The facility is surrounded by steep hills, loose shale, deep mud pits, and river crossings, conditions designed to break vehicles and expose weaknesses that would never appear in sanitized test labs. A small group of operators stands beside a lineup of off-road prototypes. These are not engineers in white coats. They're ex-military drivers, expedition specialists, overland adventurers, and desert rally veterans. Their job isn't to understand the machines, it's to break them, stress them, and translate that punishment into better designs. One of the operators, a seasoned desert racer with a voice like gravel, explains how the future of off-road doesn't revolve around horsepower anymore. Horsepower gets you stuck faster, he says. Control keeps you alive. As he speaks, he walks around a prototype vehicle with an adaptive suspension system that adjusts on the fly. Instead of relying solely on shock absorbers, the suspension reads terrain through sensors and servo systems, predicting impacts before they happen. The chassis never stays completely still. It breathes, like a living organism compensating for uneven ground. Maxwell watches as the racer straps in, powers up, and takes off toward a jagged field of volcanic rock. The vehicle glides across it, bucking, dipping, absorbing blows, yet never losing traction or momentum. If traditional off-road driving feels like riding a wild animal, this feels more like piloting a drone just above the surface, smooth and intelligent. Next, a river crossing. The operators show how amphibious kits can convert certain machines into semi-aquatic explorers. Seals inflate around critical joints, propulsion fans kick in, and buoyancy chambers activate. These aren't boats, but they don't need to be. Their job is to survive brief water encounters without catastrophic failure. In disaster zones or remote expeditions, that difference can save lives and resources. One operator invites Maxwell to examine something unusual, a tactile feedback steering wheel. Instead of relying on engine noise or body roll, the wheel communicates terrain conditions directly to the hands. Heavy drag means mud. Light chatter indicates gravel. Sudden pulses warn of traction loss. This gives future autonomous vehicles a bridge to human control. Humans don't lose situational awareness, and machines don't operate blindly. Maxwell asks about autonomy, and the operators exchange knowing looks. Full autonomy in the wilderness isn't like downtown robot access. Roads don't exist, weather changes rapidly, and hazards are invisible. So developers focus on shared control. Machines handle microcorrections, torque distribution, and path optimization, while humans make strategic decisions. It's a partnership, not a replacement. A communications specialist steps forward and discusses the next challenge: isolation. In a city, vehicles talk to satellites and cell towers. In the wilderness, those signals vanish. So they're testing mesh networking. Each drone, rover, and truck becomes a node. Together, they build a temporary communication grid, allowing them to coordinate like a digital swarm over miles of terrain. If one unit goes down, the network reroutes. If one unit climbs a ridge, it becomes a relay tower. In a few minutes, explorers can create connectivity where none exists. Suddenly, alarms beep as a storm warning flashes across a control console. Operators scramble, not in panic, but in procedure. They want Maxwell to see how machines behave when nature turns hostile. Drones deploy, scanning cloud formations and tracking wind changes. Ground vehicles switch to storm mode, lowering their suspension and tightening seals. Navigation shifts from speed to survival. Maxwell stands under a reinforced canopy as rain begins hammering the training grounds. The storm intensifies quickly, turning dust into slurry and sending debris rolling down slopes. The autonomous support rover adjusts its route to avoid flooded areas. A tracked hauler maintains traction and begins towing smaller test units to higher ground. None of this is dramatic in the Hollywood sense. It's methodical, data-driven adaptation. By the time the storm passes, the entire operation looks transformed. Mud replaces rock. Water fills trenches. Conditions are brutal, but the machines endure, learning from every second, storing telemetry for future redesigns. Maxwell watches as the operators regroup around a portable command station. They analyze storm performance, identify weak points, and suggest improvements. One operator jokes that future explorers might cross Mars or Antarctica the way early travelers crossed oceans, slowly, carefully, and with machines designed to outlive the humans who built them. Maxwell takes a slow breath. It's now clear that off-road tech isn't about adrenaline. It's about survival, data, resilience, and adaptability. And the intrigue only grows from here, because the next phase of his journey moves beyond machines and into the question that shapes every frontier. Who is building this future, and what do they want it for? The answer to that question begins near the edge of the facility, where Maxwell is escorted toward a series of black modular units stacked like shipping containers. From the outside, they look unremarkable, plain steel walls, no branding, no windows. But inside, they're humming with computation,